Well, it's been a long road. Remember, we began with the Greeks and then the discovery of the electron, blah, blah, until we got to Bohr's model that started quantum mechanics. Finally, we get to the model that's accepted today. Now, before we get into quantum mechanical model, let me tell you, this is the most accurate model that we have. But most of the time in chemistry, especially at the elementary levels that we're doing now, we're going to use Bohr's model, okay? Good enough. But, like I said, this is the most accurate model that we have, the quantum mechanical model. We saw that particles and waves are very different from the microscopic realm. They behave differently. Very soon became obvious that very, very small pieces of matter follow different rules that we see for the large objects. We talk about how you can throw a baseball and you know where the baseball is going, but when an electron is moving, you cannot predict exactly where the electron is going to be. So separating waves and particles is no longer a possibility in here. Now, de Broglie asked a very good question. If electromagnetic radiation is both particle-like and radiation, how about electrons that have a little bit of mass? Do they have a wave-like character? And the answer was yes. Okay? If you have a particle, but it has to be a very, very small particle, like an electron, that has a certain mass at a certain velocity, it does have a wave associated with it, and the wavelength is going to be calculated by Planck's constant divided mass times frequency, as also the velocity which is moving. So, yes, very small particles have a wave associated with them. That's why we had that duality. The electron is a particle and it's a wave. They're associated together, okay? And I know you cannot visualize it. It's just one of those things. You just have to take de Broglie's word for it, okay? So he was able to calculate the wavelength associated, know the particle mass, the velocity that they used to calculate momentum, and he calculated, this was supposed to be a lambda. Once again, PowerPoint sometimes changes Greek letters. Okay. But this is probably wavelength characteristic of particles. Okay. Very, very small particles. Someone decided to do an experiment with electrons similar to what they had done with light. Again, having slits, and they saw that there's interference patterns and all of that, very similar to what happened with the light. So we knew electron is a particle. We know the mass and all of that, but it's behaving like a wave too. Once again, just like light, you have a wave-particle duality in here. So the bottom line is an electron is a very small particle, but the motion does not follow the laws of motion in classical mechanics. Why? Because it's small. Instead, we're going to have a wave equation, and the wave equation doesn't tell you where the electron is, it gives you the probability distribution, a place where you're likely to find the electron. Okay? We're going to see that in all of these quantum particles. All you're going to be seeing is the probability. You can calculate probability, finding an electron in a certain area. Do you want a 50% probability? Do you want a 70%? Do you want a 90% probability? You're never going to be certain. You're never going to get a 100% probability. Okay? That makes for some really weird stuff, I'll be honest. Okay? And sometimes I'm just going to tell you, I really can't explain that. They use computers to calculate these things. That's what the computer says. That's as far as I can explain some of these things. Heisenberg said that there was a limit on how accurate you can measure both a particle position and the momentum or the speed. And again, remember, we're talking about teeny particles like an electron. Okay? If you measure the speed of the particle or the momentum very accurately, then the position is not accurate. If you measure the position, then you don't get the speed right. So that's the Heisenberg uncertainty principle. It is impossible to determine simultaneously and exactly both the momentum or the velocity and the position of a particle. Okay? Remember, we're talking about atomic particles, okay? Finally, Schrodinger put everything together in an equation. I'm glad this book doesn't give you the equation, so there's no temptation. It's a very complicated equation, Schrodinger equation, but it describes what an electron does. Okay? It thinks on the electron as a three-dimensional stationary wave. You have a wave function that explains what's happening there, represented psi. All of that is really well above what chemistry should be. What is important is that the square of this wave function, psi square, gives you the probability of finding that particle in a certain location. So that's the best that you can do. Again, you cannot locate where the electron is, but you can say there's a 9% probability it's going to be not in an orbit. Remember, an orbit we say is a path that the electron has to sit on it. No, what you have now is an orbital. The orbit we say doesn't work. You have an orbital, and maybe you come up with there's a 90% chance that the electron is somewhere in there. You know where it is, but someplace in that particular location in space. Okay, so all of this stuff we're looking together, that's what we refer to as quantum mechanics. And it's going to explain the atom, yes, very accurate, but like I said, very confusing and very mathematical. That's why sometimes you just have to say, the computer says so. That's all you can tell. So we agree that the atoms exist only at discrete energy levels, not between them. The problem is the energy level is not going to be a line, it's going to be an area of space. Okay? The energy of the electron is quantized because there can be a certain energy levels. It's going to be described, the relationship of electrons is going to be described by quantum numbers. And you have only specific levels of energy. Electrons can jump from one to the other, back to the first one, but they cannot move slowly from one to the other. They can stay between different levels. It's like right now I'm in the second floor. Okay? There's a first floor below me, there's a third floor above me, but you're not going to find me with the upper half of my body in the third floor and the lower part in the second floor. You cannot be between floors. You're in the second floor or in the third floor, right? That's pretty much what you're talking here. And if I'm in the second floor, in quantum mechanics, it says, yes, you're in the second floor, but I'm not telling you in which room you are. There's just an area where you're likely to be, but it doesn't tell you exactly where you are. That's the best I can explain orbitals. So there's 4 quantum numbers. The first one is the principal quantum number. It's represented with n, and n can be 1, 2, 3. It's similar to the numbers that Bohr used for the orbitals. Okay? The energy of an electron is greater the larger n is. Okay. And n is referred to as the principal quantum number, and some people call it the shell number, because they figure that the orbital, different energy levels are like shells surrounding the atom. We're going to see sometimes people refer to shells and subshells, so you need to be aware. Shell number is the same thing that energy level. Okay? So you have here different energy levels, 1, 2, 3, and the energy increases as you increase the principal quantum number. Other than these are not orbits, but orbitals. They're not lines, but areas. It's not so different from Bohr's model yet. But the principal quantum number is only one that's used to characterize an orbital. This could say we're not talking about orbits. An orbital is a region of the space where the electron is likely to be. Not certain. Okay? So it's not the same thing that an orbit. And the quantum mechanical model is going to just give you the probability of finding the electron in a three-dimensional space. It's vague. Yes, it's very vague. But it is what it is. Okay? Then there's a second quantum number that we call the angular momentum quantum number. Okay, it's represented by L. the values of L, well, let me slow down. It defines the shape of the orbital. We're going to see there's many shapes of orbitals. I'll show you some drawings. Some are rounded, some got dumbbells. The value of L begins at 0. Remember, n begins 1, 2, 3. L begins with 0 and goes to n minus 1. So if n equals 1, n minus 1 will be 0, so you have only one value for L. If n equals 2, then you can have 0 and 1. And you can go on and on in there. The orbitals that have the same value of n, they form a subshell. The same value of L forms a subshell. So you see suborbitals, subshells, depending what term you want to use, depending on the size. Now, to make life, believe it or not, easier, instead of using numbers, they decide to assign letters to different orbitals. Okay? You say, well, that's more to memorize. Yeah, but just a little bit, and believe me, long term, it's going to simplify things unbelievably. Take my word, okay? So when L equals 0, we call that orbital an S orbital. L equals 1 is a P orbital. L equals 2 is a D orbital. L equals 3 is an F orbital. We're going to be talking about S, P, D, and F orbitals, and sometimes we refer as electrons because they're in that particular orbitals, and S electron or a P electron, something like that. It just represents the shape of the orbital they're in. Okay? They have different shapes because we said this angular momentum quantum number determines the shape. Okay? Let me show you real quickly some of the shapes. The S orbitals are spherical. You see, we're going to go through all of this, but you can say that the L determines the shape of your orbital. Now, one of the weird things that happens with quantum mechanics is that there's certain distances from the nucleus where the probability of finding the electron is 0. And you say, what did you mean? Yeah, the electron cannot be there. Because when you solve the equation, the answer is 0, the probability is 0. And we call that a radial node. That is going to start becoming weird because, let me show you here. This is 1s orbital, no problem, all the probability is in there. But when you have 2s, you should have a 1s and a 2s. And in between them, that dark pink area is a node. The probability is 0. If you see the probability, you have probability of finding in the first one, in the second, but here the probability is 0. And if you get to C, 3s, you have 2 nodes. What they're trying to tell us is that you could have an electron that's in the 1s and jumps to the 2s, but it doesn't go through the node because it cannot be in the node. And then it's going to return to the 1s. How about if it's 1s and it jumps to the 3s, but it doesn't go through any of the 2 nodes? And then when it returns to the ground state, it returns from 3s to 1s, but it cannot go through the nodes because the probability is 0. That's what I say. Things like that, all I can say is the computer says so. The computer calculated that the probability is 0. How would you get out of your house without going through the door or through a window? No. And in the real world, that doesn't happen. In quantum mechanics, it does. Weird? Well, it can get even weirder. Look at this electron here. Oh, actually, look at all of them. The probability gets very, very small the farther you go away from the nucleus, but it never reaches 0. The only time it reaches 0 is in the nodes, which means that in mine this is a hadron atom because it has 1 electron. Mine I put it on my table. I'm in Greenwood, South Carolina. What are the chances this electron could be in Columbia, South Carolina, almost 100 miles away? It's very, very small, but it's not 0. There is a unbelievably small, but still a real possibility that that electron will be there. Again, that's a quantum mechanics. Don't try to really grasp it. Just accept it. The probability of an electron never goes down to 0 except in the nodes. And the electron is going to jump from one orbital to another, even though there is a node in between them, It's like I'm coming out of my apartment, going through the wall. But you start getting an idea that regular mechanics and quantum mechanics, they don't have anything in common. You really have to twist your mind to half comprehend quantum mechanics. We say that they have different shapes, so the s orbitals are always spherical, the p's are like a dumbbell, and we're not going to describe the d's and f's. Your instructor may want you to, okay? There was a time I worked at the college where they wanted the students to memorize the d orbitals, the shapes. I think we're going to be using these ones a lot, so it's good that you know those shapes. The other ones, it just gets to be too much. I don't see the advantage, okay? So you have an s orbital in here, circular. Here you have the dumbbell shape with, you notice that there is a node in there. So the electron is jumping from right to left without going through the center. And then when you get to the D's, notice that some are dumb shell, some, like for instance in there you have a dumbbell, but it has like a necklace. If you get into the F's, it becomes more and more complicated. I'm just showing you this as an example. These are the only ones that I want you to know the shapes. Okay? So we get to the third quantum number, magnetic quantum number. If you have basically an easy way to explain. If you have an orbital that's rounded, it only has one direction. But when you have the dumbbell shape, it actually can be oriented to the direction of the space. It can be along the x-axis, or along the z-axis, or along the y-axis. So you have a magnetic quantum number that tells you the orientation, and we call it the magnetic quantum number, and it's represented by m sub L. So now when we indicate an orbital, not only we have to give the n value and the L value, but actually many times you're going to indicate also the orientation in there. The value of m sub L is ranges from minus L to minus 2, minus 1, 0, plus 1, plus 2, plus 3, to plus L. Okay, so you always have 2L plus 1 orbitals for every L value. We said S orbitals, L equals 0. Remember, that was the circular, so you can only have one orientation of a sphere, perfect sphere. Okay? When you have 3, that means 3 orbitals, L equals 1. Remember, we said the damsel, and we said that there was 3 possible orientations. Why? Because you have minus 1, 0, and plus 1. In this one, obviously, 0 is the only value. When you have L equals 2 for the d orbitals, and we don't worry about the shape, but you have minus 2, minus 1, 0, plus 1, plus 2, so you have 5. And for 3, you have 7. This you need to know. There's 1s, 3p's, 5d's, and 7f's. Those numbers, you need to know them, although if you know the value of L for each orbital, you can deduce it very easily. You're going to have to memorize either the values of L or the number of orbitals, but one will give you the other. You don't have to memorize both. In addition to that, there's still one more thing, because so far these 3 quantum numbers define the region of the space. It tells you which energy level, which shape orbital, which orientation of the orbital, but the electron is spinning, and it can spin 2 ways, okay, clockwise or counterclockwise. So you need a spin quantum number to indicate that. Okay, it's represented by m sub s, and has 2 values, plus 1/2 or minus 1/2. And don't ask me why 1/2. I've read all sorts of theories where they come up with a number. The one that makes more sense to me is that it makes it harder to confuse with other numbers. At least, like I say, it makes sense. I'm not saying that is the real reason, but if you look at an electron, the electron in this case is spinning clockwise in here, and it's minus 1/2, and if you put in a magnetic field, it orients upwards, counterclockwise, is minus 1/2. Now, you have two possibilities for an electron. So we are going to see that every electron is going to have 4 quantum numbers. We give the energy level, the orbital shape, the orbital orientation, and the spin of the electron. Now, Pauli exclusion principle says that you cannot have two electrons with exactly the same 4 quantum numbers. That makes sense. The 4 quantum numbers are like the IDs. Remember when we talk about atomic number and we say that's the ID, there's no two atoms with the same atomic number. Well, this is the same thing. There's no two electrons with the same 4 quantum numbers. So you can have several electrons in the same orbital. They can be in the same orientation, but at the end, there's only two values for the spin, +1 and -1, so you can only have 2 electrons in one orbital. That's something very important that we are going to use a whole lot in there, and they have to have different spins. So if you have an electron, maybe it's in the px orbital, you have 2 electrons, but you can have 2 electrons in this particular orbital. That's the energy level, that's the orbital shape, that's the orientation, and in each one you have 2 electrons, but one is going to spin clockwise and that one is going to spin counterclockwise. So the 4 quantum numbers completely describe the electron. If this is confusing, I made this little table. This is my table, but this is what I want my students to know. I want you to know the name of the 4 quantum numbers, this symbol used to represent them, the values, we've been talking about different values, and what does it mean? Okay, like this talks about the energy level. This tells you about the shape of the orbital. This tells you the orientation of the orbital. This tells you the direction of the spinning. So everything that we cover about quantum numbers is summarized in this table in here. Okay, if you memorize this table, you know everything you want to know about quantum numbers. I do have some examples to practice, so if you like to get any of my worksheets, if you have questions, remember you can make an appointment through Wisant. The link to it is in the video description. I'd be glad to meet with you and practice until you feel comfortable. And remember, you're not expected to really understand it. Quantum mechanics is, okay, this is it. It's been written by a computer and we just have to accept it, okay?